solid states. So we know what liquids are, we know what solids are, we know what gases are. These slides are just going to kind of regroup what you know about a liquid. The only thing I don't know that you understand is the word translation, translational. So I think you understand vibration, right? So look at my hands, vibrating molecules, right? And then rotational is rotating molecules, which means that they just must have sigma bonds, not pi bonds, right? Because pi bonds could do a little bit of that. So rotational, but then translational is like this, passing each other, right? So when you have a liquid, particles undergo translation with respect to one another. They can move past each other. Slide, you know that a liquid can move. The particles are still held closely together. They're not in the gas phase. And then here are solids. They definitely don't have translation with one another, right? A solid doesn't move past itself. Its rigid structure doesn't allow for that. It can still vibrate, for sure. Molecules are vibrating. They all have some kinetic energy related to them. All right, this word amorphous solids, I want you to sort of think of, and I kind of use the idea of slime, but slime maybe isn't very, I don't know, not a great example. Rubber is a better example, but think of those as they're being formed. So if you're pouring rubber or something into a mold, you can think of that as a very viscous liquid, right? Or even after it's become a solid, it really has no shape to it in a sense. The molecules themselves don't have good alignment. They're not organized. They're just sort of blobous. So I try to think of it as slime, where it doesn't have nice arrangements of the molecules. They're just sort of all there. So macroscopic meaning it's large. It's not microscopic. It has not great shape and not very well-defined faces. They don't stack well together, and examples are glass and rubber. Then you have crystalline solids. So the crystalline solids are like ionic solids. Anything that has neat organization, has a lattice structure, so they line up with one another, those are going to be considered your crystalline solids. So it gives you an example. Quartz and ionic solids are crystalline. All right, so this whole section we're just going to get rid of. So with molecular solids, these are nonmetals, diatomic elements, or compounds composed of two or more nonmetals. They normally do not conduct electricity, as electrons are held with the covalent bonds of each molecule. Covalently bonded units are held together by intermolecular forces. As such, forces are relatively weak. These solids are soft, have low melting points. So when I'm talking about a molecular solid, maybe I'm talking about iodine. So iodine exists as a solid at room temperature. Bromine exists as a liquid at room temperature. That's like Br2, I2. But then fluorine and chlorine exist as gases at room temperature. Why is that true? Going down the group, fluorine, chlorine, bromine, iodine. Iodine becomes a solid at room temperature. Bromine's a liquid. Why is that true? We're talking about intermolecular forces. So what kinds of forces do they have on themselves? London dispersion forces. And the stronger your force of attraction, right, the state of matter at the same temperature is different. So why?
It's a higher temperature because
they're more polarizable. They have more electrons. Iodine, I2, has more electrons than Br2, Cl2, and F2, right? So the more electrons you have, the more polarizable it is, therefore your London dispersion forces are stronger. Everybody got that? So that's what a molecular solid, we can consider that to be. But it's still held together by intermolecular forces. It's not different than anything that we talked about before for intermolecular forces. Here's another example of a molecular solid. So these are, it's talking about how the shape of these molecular solids plays a role in their physical state. So these are fats, like butter and margarine. So you have saturated fats. The way I try to remember them is if I'm saturated with something, like saturated with water, I'm drenched in water. This is a saturated fat because it's saturated in hydrogens. It's drenched in hydrogens. So this structure can stack up neatly, right? So it has London dispersion forces with itself. It's stacking up neatly, so it is a solid at room temperature. What about this one? Does that stack up neatly? What happens right here? What kind of hybridization do you have around that carbon? Bent, right? Well, not bent, trigonal, planar. Do you see that? So you have a kink in your structure. You don't have a flat line. You have a kink. So it looks like this. So when your London dispersion forces are trying to build on top of each other, that's throwing the hangers in the box, right? You have nice, neatly stacked hangers. You have coat hangers thrown in the box. So this one is not going to have great attractive forces because it's trying constantly to get all those kink bends to attract to one another. So this fat, unsaturated fats, are liquids at room temperature. The industry prefers to use saturated fats because these things are super stable. They never go bad. Their London dispersion forces hold them tightly and pack them neatly together. So margarine lasts forever. It doesn't go bad essentially, right? Whereas this one has this site right here. You can have oxidation occurring, which means it's going to break that. And if you're breaking those bonds, you're creating new molecules, which essentially means your butter goes bad, right? So over time, it would go bad if it's sitting out on your counter, whereas this one won't go bad. The problem with this being margarine, a saturated fat, is it has no nutritional value at all, no energy that you're going to use from it. Your body basically just puts it into your stomach, it absorbs it, and this is a fat, and we know that likes like, so where does your fat go? Into more fat. So you eat this fat, and then your fat just dissolves more fat in itself, so you get fatter. And then if it's not going in your fat, then it's just taking out fat-soluble vitamins and nutrients that you get from other food. So now it's sucking away all the good stuff, and then you deposit it elsewhere as it comes out of your body. So it has zero purpose in your system. It's nothing. It's horrible for you. Even though this is fat, at least it can be broken down in your body and not necessarily absorbed right back as fat. So this one is definitely better for us, but it does go bad on your counter. All right, covalent network solids. This is the key thing to ranking any substance that I give you. The very top of our chain now is a covalent network solid. So that's diamond, that's graphite, that's glass. All of these phrases that I'm just throwing out at you, words, are so that you have to memorize the specific ones that are covalent network solids, and then you're fine. You're golden for answering any questions as long as you recognize them. So I don't think you know them, which means that you should probably make a quick little note card of them and make sure you know the names of them, because when you see them, you need to recognize this one's a covalent network solid, so it's going to have the highest melting point, boiling point. It's going to be the strongest. So it says when a covalent network solid is when one or two nonmetals are held together by networks of covalent bonds, not intermolecular forces. So if I have a covalent bond, my shoulder to my arm, literally the strength of this is so much stronger, we know that already, than intermolecular forces. So you have essentially a huge macromolecule, not little minuscule, a macromolecule. My diamond on my finger, right here, is an enormous macromolecule, one diamond molecule, one of them. No intermolecular forces. It's carbon, sp3 bonded to 4 other carbons. So diamond is one massive molecule over and over of all the carbons attached to each other through sp3 hybridization. Everybody following what I'm doing? I'm just continually bonding it to carbon. So there is no need for intermolecular forces because it's just covalently bonded to itself. So it's this throughout the entire thing. Strong forces, no forces, strong bonds. When you look at the carbon group, the elements in carbon's group are the ones that will covalently bond through a network solid. So take a look, either periodic table or your own. As you go down the group, you have carbon. That's going to be carbon to carbon to carbon to carbon, 4 bonds. Silicon can also bond 4 times. So the silicon group, like SiO2 and SiO4, those are examples of a covalent network solid. I have seen them, I think, once or twice on the AP exam use germanium as something. And I don't know that all of my students were familiar with it because they usually use diamond and silicon dioxide and graphite. But if they throw a germanium at you, or they throw tin at you even, they might put a tin example, then you have to recognize that that could possibly be a covalent network solid. So all of them are extremely strong because they have the covalent bond. So here's an example. We're good with carbon, right? Diamond, it's all sp3 hybridized. If you get a question, I think you might even on your homework tonight as to why diamond is the strongest, The specific reason is because it's covalently bonded through sp3 hybridization. You need to note the sp3 hybridization. That means carbon bonded 4 times some more carbon, right? The next slide is graphite. So after diamond, graphite is extremely strong. Graphite is in your pencil. So as you're writing right now with your pencil, you have covalent network solids. It is also carbon bonded, but 3 times. So it's carbon to carbon to carbon with sp2 hybridization, and it has a lone electron right here. So you end up creating, here's your electron, you create these sheets with these lone electrons sitting on top of them. So they're sp2 hybridized, and these little lone electrons are sitting in an unmorphed p orbital. So you have a p orbital with them in there, and p orbitals, right, we know are these side-to-side sort of situations. And so the electrons that are there are going to create London dispersion forces with the next sheet. So you have a graphite sheet here, then you have another graphite sheet here, and graphite, and they all layering on top of each other. They are still macromolecules, but they're held together through intermolecular forces between each of the sheet by London dispersion forces, holding them together through those pi orbitals. So here's a picture of them sitting on top of one another. It says delocalized pi bonds are between the sheets holding them. So when you're writing with your pencil, the sheet is coming off and creating new intermolecular forces with your paper, and that's why it sticks on the paper, right? And then the next sheet will come off. You can also envision that if you took graphite and you grind it up, you would get powdered graphite. Do you agree with me? So one of the examples that they often use is they will give you a bunch of choices, and they'll say the following can be used as a lubricant. Graphite is the correct choice. Jot that down. Graphite is a lubricant. So like locksmiths will have graphite and put it in the lock if it's not working correctly to lubricate it. Graphite. Guys, do you know who MacGyver is? No. What do you guys watch? What cool shows are there where someone makes like a bomb out of their little, I don't know, they have a watch and they're trying to get out of like a secret lab and they have to escape, and he like made all these things out of nothing. Like he'd take a rubber band and all of a sudden he had a key. Huh? Flash. Okay. There we go. So Flash would probably carry graphite with him.
I think vibrate.
Oh, so he has superpowers. See, MacGyver was really cool. He had no superpowers. He was you, but just super smart because he had like every skill imaginable, and he could make anything out of anything that was lying around. Should check out some old episodes of that. And Karate Kid.
I just watched the Group video.
You just watched my videos. Thank you. There you can learn almost nothing besides chemistry. All right, so you got your sheets on top of each other. The only thing else I want to say about this is when you have these delocalized electrons in the pi bonds, you can conduct electricity. Remember, electricity is always because electrons are free to flow, or there's ions kind of molten or in solution, right? So if you have a free-flowing electron here, you can conduct some electricity. You guys are going to jot that down? Jot that down. Some electricity?
Can you repeat that?
No. You can watch the Jabru Guru videos, Mike. Pi bonds conduct electricity because the electrons have movement. Not a lot, but they have some movement. Here's a picture of that. So here's all your p orbitals, unmorphed p orbitals. Here's your sheets, 3 sheets. And then you have a little electron in this p orbital that can freely move through the sheets. So if you have electrons free to move, then you have the ability to conduct electricity. They also have very high melting points because each of these layers is a covalent network solid. All right, the next few are just covalent network solids. It's giving you more examples of them. Silicon dioxide, the SiO4, any silicon group, and then I said to you, if you look at the periodic table, germanium and tin are often used as examples. All right, so we're going to get rid of all of the semiconductor slides. A metallic solid is literally just metallic bonds, right? So it can be an alloy, or it could be a metal by itself, just attached through metallic bonding, the sea of electrons. But where you rank this is sort of tricky. So I'll show you in a moment my ranking list. But I would say, because most of the time I would think of metals as not being like the smaller atom size metals, I'm usually thinking of larger ones. And it kind of makes sense, right? Like table salt, sodium chloride, its boiling point, or its melting point, let's just say melting point, is quite large, right? If you try to melt iron, that automatically should be obvious to you. That's going to have a much higher melting point, right? So most metals, I will say, are going to have a higher melting point than most ionic solids, but you certainly can have the reverse scenario happen. You can have metals that have lower boiling points than ionic solids. So where they rank, if you go from a covalent network solid, then the next strongest would be a metal, and then the next strongest would be ionic. Realize that the metal and the ionic bonds, they could certainly flip depending on the substance. Right, like an alloy, a metal alloy, alloys are always typically stronger than the individual atoms that they come from. A steel bridge is certainly going to have an incredibly high melting point, right? That's going to be much, much stronger. So some metals are definitely going to have a higher ranking than any ionic bond. So bonding is not covalent. It's between two or more nonmetals, or one metal with itself. The way that you can talk about the bond strength is based on how many electrons are in after its noble gas configuration. And this is what this is showing you. If you look at sodium, its noble gas would be neon and then sodium. So it would have one electron, right? We call that the valence shell. But if you're looking at what iron's doing, it's counting its 4s2 and then its 3d6 electrons to give you a total of 8 electrons after its noble gas. Do you see how that works? So the more electrons you add, the stronger the bond becomes. There's more electrons free to flow, and more of them are attaching to the nuclei inside each of the metallic atoms. So you create a stronger metallic bond. The stronger the metallic bond, the higher the melting point, boiling point, all of that. So here's just a visual representation of metallic bonding. What you guys need to recognize is that the electrons, this is really spread out. It should be much, much closer together. But the electrons that are in these valence shells out here, and these are the nuclei, are attracted to the other nuclei nearby. So they're really compact on top of one another. It's a solid, right? So this electron is free now to move here, and then it's attracted here, and then it's attracted through all of them. So the electrons just start moving all over the place, not with their original atoms that they were with, because they're attracted to the nuclei that are adjacent to them. And then they just keep moving and moving and moving. So they're able to conduct heat and electricity. They have no directional bonds. Metals tend to bend. They don't shatter if you hit them with a hammer. Because ionics, right, you have positive and negatives, and if you hit them with a hammer, they adjust, and then they repel each other, and then they shatter or break. But in this case, the electrons are moving all around. They're attaching to all the positive nuclei, so they're likely to just bend and be moldable. I think that was it, right? It's the last slide. So this is the last thing I just want to show you. So you should have this ranking system down kind of by heart before you take any test on intermolecular forces. Even when you're doing your homework, I would use this as my general guideline. I'll give you a minute to write it down. Can you just listen? Just look at the board and watch. First thing you do, if you're looking at any of them, is you tell yourself, is it a covalent network solid? So it's either going to be diamond, it will literally say diamond, or it may say C, and then it'll write diamond as a subscript. Or C, and then it'll write graphite as a subscript. So you're looking to see if it says diamond or graphite, silicon dioxide, it might say glass or quartz, and then remember it could be any of the group 4 atoms included in some sort of combination with them and oxygen, kind of like SiO2. Beneath the covalent network solid, I'm going to place the metallic, but realize that these two can change based on the strength of the bonds of either the ionic or the metallic. So for a metallic, you're looking to see that it is a metal and a metal, either a metal by itself or a metal with another metal. Ionic bonds, you know, are non-metal with metal, right? And then from there, the rest of them that are non-metal with non-metal are going to be ranked as your covalent bonds. And then you're going to look at their individual forces like we've already discussed in the beginning of intermolecular forces. So we basically just use this the whole time from today and forward, you have to see where it falls in this list and then determine its melting point and boiling point. Is that clear?